Now we will start with the first decoupled method of load flow solution. This is the last lesson on module 1, load flow analysis. First decoupled method of load flow is based on decoupling of real and reactive power P and Q. And why such decoupling is there in the power system? That's because power system transmission lines have a very high X to R ratio. For such a system, the real power changes delta P are less sensitive to changes in the voltage magnitude and are most sensitive to changes in the phase angle. Similarly, reactive power is less sensitive to changes in the load angle and are mainly dependent on the change of the voltage magnitude. So it simply means that we have a P delta and QV coupling in the power system. But remember that these are not completely decoupled, but for practical purposes we can consider them to be decoupled. Therefore, it is responsible to state set elements J2 and J3 of the Jacobian matrix to 0. What were J2 and J3? J2 was about dependency of the real power on the voltage magnitude, whereas J3 was related to the dependency of reactive power on the load angle. Okay, and these two can be cancelled, or writing more clearly, delta P delta V and delta Q dou delta, this must vanish when we are obtaining the load flow solutions, or if we put this to 0, the accuracy we obtain from the load flow solution is admissible. Now this results in two equations. Delta P is equal to simply J1 delta delta and delta Q is simply J4 delta V, or the delta P, the change in the voltage magnitude, is dependent on the partial derivative of the P equation with respect to the load angle into the change in the load angle. Similarly, the change in the reactive power is equal to the partial derivative of reactive power with respect to voltage magnitude into the change in the voltage magnitude. Now, this is known as decoupled load flow. Okay. To make it fast decoupled, we can make further assumptions. So, what are the simplifications? Equations 2 and 3 show that the matrix equation is separated into two decoupled equations, requiring considerable less time to solve. Further simplification can be made to eliminate the need for recomputing J1 and J4 in each iteration. The computational requirement of the Newton-Raphson method is that every iteration we need to compute the inverse Jacobian, or we need to compute the Jacobian and find its inverse. So we want to find a way that we can compute the Jacobian only once and use it for the whole of load flow computation. In that endeavor, we get the equation for dou Pi by dou delta, replacing the first term of the equation with Qy. So this is basically Qy. So we get dou Pi by dou delta as something simply reactive power minus voltage square into the fixed element which can be obtained from the Y bus matrix, or it is simply Y bus sin theta, which is the imaginary part of the diagonal elements of the bus admittance matrix. In fact, BII is the sum of susceptance of all the elements incident to bus I. Okay. Now, in a typical power system, the self-susceptance BII is much larger than QI. Therefore, neglecting Q and assuming in per units, of course, VI square is equal to VI, because VI is nearly 1. So, VI square should be equal to VI. Further simplicity is obtained by assuming Vj is equal to 1. Okay. And then we get these two expressions. Okay. Similarly, the diagonal elements of J4 may be written as like this, replacing by Qi, obtaining del Q by del Vi, we get this equation. Since Bi Yii sin theta is much greater than Qi, and assuming the difference between the load angles between bus I and bus J to be very small, we find out these two equations. And then we proceed towards the first decoupled load flow algorithm. So, with the assumptions as above, our original decoupled equations, these 2 and 3 are original decoupled equations, they become simply delta P by Vi minus P dash delta Q by Vi P double dash delta. This is the final expression as obtained from the Harisadat book. Here B dash and B double dash are imaginary parts of the bus admittance matrix. Since the elements of the matrix are constant, they need to be triangularized and inverted only once at the beginning of the iteration. Okay, so only once. B dash is of the order of n minus 1, B double dash is of the order of n minus 1 minus m, where m is the number of voltage regulated buses. For voltage controlled buses, where Vi and Pi are specified, Qi is not specified, corresponding rows and columns of I bus are eliminated. Then successive voltage and phase angles then can be obtained as change in load angle, change in voltage, simply by multiplying this with the change in real and reactive power. So, no more computation of the Jacobian in every iteration. And this is known as the first decoupled load flow. Towards the end, we will see the difference between DLF and FDLF. So, what are DLF, FDLF, and a new term DC load flow? What is the difference between them? Now, decoupled load flow or DLF method separates the P delta and QB equations, acknowledging real power changes is affected by the load angles, and reactive power changes mainly affect the voltage magnitudes. Jacobian submatrices like B dash, B double dash are re-evaluated or updated during iterations. So, we update the Jacobian submatrices in every equations, though less frequently than the full Newton efficient. Okay, because we have made many approximations and made this decoupling part, and J2 and J4 have become 0, J2 and J3 has become 0. Whereas first decoupled load flow is faster and simplified version of the decoupled load flow method, achieved by making stronger assumptions, primarily treating the Jacobian matrix element related to B dash and B double dash as constant throughout iterations. So, if the coefficient matrices are constant, the need to update the Jacobian at every iteration is eliminated. And the reason for that, as we have already seen, that the susceptance value is much more than the conductance one, the voltage angle difference is nearly 0, and Qi is much less than Pii Vi square. Because of these three reasons, we can convert the decoupled load flow to first decoupled load flow. Beyond this, what is DC load flow? It's a further extreme simplification, mostly used for planning studies, ignoring reactive power entirely. Okay, that means constant voltage and resistance 0 for very fast approximate solution, ideal for contingency as well as planning analysis. Okay, now this is one example taken from the Harisadat book. Okay, so how it is solved? Using the first decoupled method. Okay, first you need to obtain the Y bus matrix. So, I have given the solution in 2 steps here. The code for this solution is available in your laboratory as a laboratory question, and the code is provided. You can solve that. So, when you use that code, you can find similar kind of results for obtaining or implementing the first decoupled load flow. So these are the iterations 1 to 14. Then what are the various magnitude changes? Delta 1 is slack bus, change in load angle, voltage magnitude, and V3 is not there because it's a voltage control bus, change in real power, and finally change in the reactive power is Q only. Okay, so this is provided. Okay, so we will see that soon. Okay, so for that you can refer to the code that is provided. Let me see, I'm trying to show you the MATLAB. Okay, somehow I cannot show you the MATLAB. Yes. Okay, now you see this is the MATLAB and this is the code. I'll try to just run this, we'll clear it. Okay, so now we are going to run this code. Okay, so if you see here, this is this code, this problem belongs to the Harisadat book. So this is the code. Now I am trying to plot this variation. See here only B11 and B22 are used in this code. So I'll show you the result. So I have cleared the screen. Now let's run the code. So as you can see, the results are obtained here, including the power flow S1, and this is the result of the iteration. Okay. Now we'll go to the final slide. So load flow is a very complicated program. It's very difficult to write load flow problems or load flow algorithms for large bus systems or where the number of buses are very large. So to solve that, we have one software known as a MATPower, which is free and open source. It can run both in Octave as well as MATLAB. So it can be obtained from this website. So as we can see here, this is from the Octave software. This screenshot is from the Octave software. So define constants has to be noted. Then you decide base MVA, load flow using MATPower. So here you use a start file where you load the case. So case 30 in this case means 30 bus system. Then you give the MATPower some options like what kind of algorithm you are going to use. Here it is NR, Newton Raphson. Whether you want to show everything in the results. So for that verbose and out all. So enter the choice load flow and OPF. So I have written the code like that. So as you can see here, so run OPF command can be used to run optimal power flow, whereas run PF simply runs the load flow. Okay. So this code is included in your power system laboratory to run it and understand the code. So with this, we come to the end of the first decoupled load flow method of load flow solution, the FDLF algorithm. And this also completes module 1, that is power flow analysis. From next class onwards, we are going to start with economic dispatch. Thank you all.